Our last part in section 8.4, and that was the ratio test. And I want to finish up that example, and then I'll open up the floor for any practice problem questions. But what the ratio test is good for is the ratio test is really good when you have a series with n in the power or some sort of a factorial. Okay. So when you look at a series and you see a series that has a factorial or possibly an n in a power, then your first thought might be, oh, let me think about the ratio test. And so the example that I left you with last time was the example of the sum where n goes from 1 up to infinity of n factorial over negative 100 raised to the n. And so strategy-wise, when I look at this series screams ratio test. Because when I look at it, first of all, I see an n that's in a power, and I see an n factorial, which means, that's a double dipping on the ratio test. So I absolutely positively want to use the ratio test for this particular series. Now, what exactly does the ratio test say? Well, the ratio test says that we want to look at the limit as n goes to infinity of the an plus first term over the an term. Okay. So in terms of notation, I'm looking at a series that looks like the sum of all the an's. And I want to calculate the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. And so if this limit is greater than 1, then the series diverges. And if this limit is less than 1, then the series converges. And if this limit is exactly equal to 1, we know nothing. So the test fails. Now, there's a lot, all these series tests that we're learning and things that are going on, there's all kinds of rules that go along with all of these. And as you're sort of trying to organize them in your head, what you might do is think of this along the same lines as the geometric series test. When we identify with the geometric series, we look at the r value, the ratio value. And when r is greater than or equal to 1, then we know that our series is going to diverge. And if r is less than 1, then the series converges. And so this is a very similar test, but we have a little bit of a weak link in that when our limit ratio is equal to 1, we don't know anything. But otherwise, it's a very similar set of rules to the geometric series. Okay, any questions about this particular test? We went in detail on it last time. This is just a reminder of what it was. Okay, so let's take a look at this particular series. I see a factorial, I see an n in the power, so I definitely want to apply the ratio test. And so I'm going to set up my limit as n approaches infinity of an plus 1 over an. And so as I write this out, an plus 1 says that I'm going to look at my terms. I'm going to cover up the series symbol and look at the terms, and everywhere I see an n, I replace it with n plus 1. So we've got n plus 1 factorial divided by negative 100 raised to the n plus 1. And all of that is divided by an. So I look back over at my series again and I cover up the summation sign and say, okay, everywhere I see an n, I just leave it as it is and write down n factorial over negative 100 raised to the n. And so I'm taking the limit of this really, really bulky fraction, and I have absolute value bars around it. All right, are there any questions about setting that part up? After I've done about 3 of these maybe, I realized that this very first step is kind of a waste of a time step, that I might immediately go directly to writing this as the limit as n goes to infinity, and rewrite it as multiplying by the reciprocal rather than writing out this really complex fraction that I have here. And so I've got the limit as n goes to infinity of n plus 1 factorial over negative 100 raised to the n plus 1 times negative 100 raised to the n over n factorial. Okay, so our goal is to analyze this limit and determine whether the value of that limit is greater than 1, less than 1, and hopefully not equal to 1. Okay, so what is one thing that I can do with this expression here to start to maybe think about doing some canceling? Okay, which n plus 1 do you think?
The one in the power, split it up into 2.
Yeah, so this is a really good place to start. We've got negative 100 raised to the n plus 1. Let's rewrite that as negative 100 raised to the n times negative 100 raised to the first. Alright, so we've done that, and that's going to be really nice because that's going to allow us to cancel the negative 100s to the ends. The other thing that we can do is that this n plus 1 factorial, I can rewrite that. And so over to the side here, just to remind you about that, n plus 1 factorial looks like 1 times 2 times 3 times, and we keep on going, and my very, very last term is going to be n plus 1. Which means that the term right before that, one number less than n plus 1, is n. And so this whole beginning part here, 1 times 2 times 3 times blah, 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 all the way up to n, is the same as n factorial. So I can rewrite n plus 1 factorial as n factorial times n plus 1. What I cannot, absolutely positively cannot do, is take this factorial and distribute it through the parentheses and write it as n factorial plus 1 factorial. That would be an absolute positive illegal algebra move, so please do not do that. Okay. So, alright, so when we rewrite an n plus 1 factorial, I can think about saying, okay, I'm going to multiply 1, 2, 3, 4, blah, 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 all the way to n, and then times n plus 1.
So if you had an n plus 3, it would be n plus 3, n plus 2, n plus 1, and then all those.
Yes, that is correct.
Okay.
Yes. Good. Other question? Okay. So now that we've rewritten everything, a lot of things are going to cancel. The n factorials will cancel. The negative 100 to the n's will cancel. And it looks like we've got ourselves the limit as n goes to infinity of n plus 1 divided by
Negative 100.
Thank you. Negative 100 raised to the first, which is just negative 100. Okay. So now I look at this expression here, and if I didn't like that negative, I could certainly get rid of it because I do have those absolute value bars, so I don't care about that negative sign, and I can be sloppy with it and just knock it out. But let's take a look at this overall ratio that we have. We want to look at what happens as n goes to infinity. Our denominator stays the same. What happens to our numerator? It's getting big. So we have big divided by a fixed number tells us that our limit is going to be equal to infinity. So here's the question. Is infinity greater than or smaller than 1? Tough question. Tough question of the day.
It's smaller.
That would be incorrect. So infinity is greater than 1, so our series diverges. All right, any questions about this example?
methods, like if, for example, you got equals 1,
Mm-hmm.
which would be the next test that you would give to?
So most commonly, if you're going to get a value of 1, it means that you haven't kind of followed your strategy correctly. And so if you get a value of 1, chances are good that you were looking at something like maybe n cubed plus 3 over 3n to the 4th plus 2, or something like this. And so notice here that our n's are all in the base. And so really this type of test, you're going to get a ratio of 1. So the ratio test is always going to bomb on something like this. Rather than that, on this type of test, this looks like a p-series. So I'm probably going to look at the limit comparison test.
You convert that all to function, take the limit, blah, blah, blah.
Right, so my limit comparison test says that I need to find a known series, and likely my known series is going to be the sum of n cubed over 3n to the 4th. I look at my top and bottom powers. I can simplify this to the sum of 1 over 3n. I can factor out the 1/3. So my known series would be something, it would be a harmonic series, and then I would compare that and figure out if my two series are comparable or not.
So if you start with the right places, that won't happen.
That's correct. That's the moral of the story. Yes, you won't get a value of 1 unless it's the wrong test too. Okay, other questions about this?
So,
Can you get, oh, sorry.
Go ahead.
Can you
No,
get
go.
0 out of this test?
Can you get 0 out of this test?
So does that count as?
No, because the only way that you would get 0 out of this test is if you had 0 in the numerator. And that's only really going, well actually no, that's totally wrong. You can totally get 0 out of this test.
Does that count as?
Right, I mean you could end up with, if we had flipped this thing upside down, and we had the n factorial on the bottom, then this ratio would have been upside down, and we would have had a number over n plus 1, and then this would have gone to 0. And so that's certainly less than 1, and so the series converges. Good.
I forgot. That's okay. I'll think of it.
Okay, other questions about this?
This is kind of after the thing, but right there, if you went, it would just go to 0, right?
Which one?
The limit comparison test?
This one here?
Yeah. If you had infinity, it would be 1 over infinity.
So the terms go to 0, but the series does not necessarily converge. So if I rewrite this one more time, I can write this as 1/3 times the sum of 1 over n. And this is the harmonic series which diverges. So even though the terms go to 0, when the terms go to 0, we know nothing about the series. The series could converge, could diverge.
So that would diverge.
This particular series diverges.
Just because of the harmonic series, that always diverges.
That's correct. It's a p-series with p equal to 1.
Yeah, all right.
Okay. Other questions? All right, I'd like to open up the floor to 1 or 2 practice problem questions if anybody has any.
On number 19,
In 8.4?
in 8.4, it seems to me that 2 different tests are giving me 2 different answers.
Well, that's not good.
I know, so I did the ratio test and I found that it diverged, but then it seemed by the alternating series test that it converged.
Okay, so let's take a look at those 2.
Maybe to start with the alternating series test because the book says it diverged.
Okay, so let's take a look at number 19. And we have the sum, this is in section 8.4. The sum where n goes from 1 up to infinity of -3 to the n over n to the 3rd. And so one option here is to use the ratio test. And the other option is to use the alternating series test. So when I look at this, because I see an n that's in the power, my first choice is going to be ratio test, and that's the one I want to use, and that one ended up giving you the answer that matched the book. So we'll leave that one alone, but that is where I would start. But it's also valid to look at the alternating series test. So let's look at that one. Alright, so the alternating series test says that you have to have an alternating series, a series that bounces plus minus plus minus. And if I rewrite this series so that I have the sum where n goes from 1 up to infinity, and I split up this power on the top so that I have negative 1 to the n times 3 to the n divided by n to the third, then I can see that I have an alternating series because I have this plus 1 minus 1 plus 1 minus 1 part that's going on. So it's legitimate for me to look at the alternating series test.
Okay, that's where I went wrong, because I put the alternating part as the minus 3 over n.
Yes, so yeah,
Okay,
the alternating
so now
part
I can
is
see where it would totally go wrong.
cool. Okay, well I'm going to keep going because I think this is a valid thing to talk about anyway. So when I look at this series, here's my alternating part, and the alternating part is just the plus 1 minus 1 part. And so my non-alternating part that's what we call Bn, and that's going to be 3 to the n over n to the third. And so the two things that I need to check to make sure that, number one, Bn plus 1 is less than Bn for all values of n, and second, that the limit as n goes to infinity of the non-alternating part is equal to 0. So these are the two things that I need to check, and if I check both of these and I come up with yes on both of those, then we can conclude that our alternating series converges. So if yes to both 1 and 2, then our series converges. Now this is not an if and only if statement. And so if we get no to either statement 1 or statement 2, then the alternating series test tells us absolutely nothing. So if we find no for either statement 1 or 2, then we know nothing from the alternating series test. So if you ever find yourself saying the statement, by the alternating series test, the series diverges, then you know that that's a wrong statement to make. Alternating series test can only show that a series converges. Okay, so let's take a look at what we have here. So our check here, Bn plus 1 is less than Bn for all n. So if we look at that, then we're looking at the question of, is 3 to the n plus 1 over n plus 1 cubed less than 3 to the n over n cubed? Aaron, you say no. And what do you say no?
Because it's the top, the n plus 1 is bigger than 3 to the n.
Yeah, I mean, we are still dividing by something that's a little larger over on this side, but even if I check, say, for example, well, let's go with maybe a 3 or a 4. Let's go with a 3, for example, over here. If I look at n is equal to 3, then I've got 3 to the 4th divided by 4 to the 3rd, and is that less than 3 to the 3rd over 3 to the 3rd? Is that true? The right-hand side is equal to 1. What is 3 to the 4th?
81.
Yeah, that's 81. What is 4 to the 3rd?
64.
Yeah, so 81 over 64 is definitely bigger than 1. And so right here, even if I just look at n equals 3, this statement right here is false. And so the answer here is No, so our first line fails, and that means I can't use the alternating series test.
So the alternating series test, you have to break the alternating part down to a very minimal,
Yes.
like the most basic part of the alternating part.
Yes, so,
Okay.
so the way that you want it to look is you want it to, your alternating series to look like the sum of -1 raised to some power times
Okay.
the non-alternating part. Yes. Yeah, I wasn't very clear on that last time. Okay, other questions?
I was just thinking, it seems like when you're using assessment, it's almost just faster to try step 2 first. And that's really usually to figure out, so.
Yeah, absolutely. I think that step 2 is probably the quicker one to look at than maybe step 1 even. But you, I mean, so if you get a no for step 2, then chuck it and go a different route. If you get yes on step 2, then you have to go back to step 1 and convince yourself of that. Yeah, absolutely. As long as you can find one of these 2 that fails, you want to throw the test out.
So if that appeared in the denominator, would it be the same?
The -1?
In the
Sure, because
Okay, all right.
-1 to the n over 1 is the same as if I
Right.
put the -1 in the denominator, so, yeah. Other questions? Okay, other practice problems, I can take one more. Twice. Is this it?
Part D on 39.
So for which of the following series is the ratio test inconclusive, that is, it fails to give a definite answer? So we've got somewhere n goes from 1 up to infinity. That was sad. Somewhere n goes from 1 up to infinity of the square root of n divided by 1 plus n squared. And the question is, does the ratio test work or fail on this series? All right, so what were your thoughts when you were looking at this?
Well, I mean, I just had a hard time, I guess, getting it to a point where it made sense. It just seemed like it kept getting more and more messed up. So I think my algebra was what was holding me back.
Okay, so the first thing when you're looking at this is, as soon as I mean, the quick answer to this question is that when I see this and I notice that I only have n's that are part of the base, then I don't want to even go near the ratio test of this one. And so when you're working on this, if you do all the algebra and work it out, then your limit as n approaches infinity of the an plus 1, which would be square root of n plus 1 over 1 plus n plus 1 squared divided by square root of n over 1 plus n squared, that after quite a bit of work, you're going to end up with a value of 1. And that's always going to happen when your n's are just in the base. And so in this case, the ratio test will end up failing. I think if you are working through the algebra of it, when you flip this upside down, then you can rewrite this as the limit as n goes to infinity of square root of n plus 1 over 1 plus n plus 1 squared times 1 plus n squared over the square root of n. And so this can get pretty ugly, but one thing that might help with your algebra, if you do want to work this through and get that failed answer of 1, is that you can regroup and put the square root of n plus 1 over the square root of n, and that ratio is going to go to 1. And then this term over this one down here, if you multiply this out down here, the biggest power is going to be an n squared, and you can compare that with this n squared, and so this ratio is also going to be 1. Okay. All right, does that answer your question, sister?
Yep.
Okay, cool. Alrighty. So that brings us to the end of section 8.4. And so for those of you that have been working on these practice problems, something that you might notice is that this list of series tests that we have is getting really long. There's a long list of tests to work with. Our toolbox is quite full, and it was very empty just 2 weeks ago. So there's a lot of new information that you have been learning. And so I'd like to spend the last part of this hour and the first 10 minutes of the second hour giving you an opportunity to work with some of these series. So I handed out a sheet that's called Looking for Patterns in Series. If you came in late, I have one here. And so when I look at this series, maybe one thing that I notice is I do see a -1 raised to the n. So one option is I could think about an alternating series test because I see the -1 to the n in there. Another option when I look at this series is that I notice that there are n's in all of the powers. Now, I don't really care about the -1 to the n. That n in the power isn't really what I'm focused on, but there are n's in powers all over the place in here as well. And so when I see n's in powers, what test might I think about? Yeah, the ratio test would work. So I could work on a ratio test because I see n's in the power. And this particular series here, because n is in every single power and there's no addition going on, this one actually turns out to be a geometric series. So you could also even look at this one as a geometric series because the n is showing up everywhere, there's no addition, it's not like a geometric series, it is in fact actually a geometric series. So you could write out the terms and figure out what the a value is and what the r value is equal to as well. The test that I would personally recommend on this one, and I tend to like the ratio test a lot because as long as you don't get stuck in the algebra in the middle, the ratio test gives you a final conclusion that you don't really have to wave your hands at all. And so if I was looking at this, I'd probably immediately go for the ratio test. All right, so one thing to think about when I'm setting up the ratio test, so I'm just going to write this down. We've got the limit as n goes to infinity of the absolute value. And I'm going to skip that first step where I write the fraction as a really, really big fraction and just do an plus 1, which is -1 to the n plus 1, times 2 raised to the 2 times n plus 1 over 5 to the n plus 1. And I'm going to multiply by the reciprocal of the an. So times 5 to the n over -1 to the n times 2 raised to the 2n. So I'm not going to continue with this one. I'll let you work on it, and if you want to ask about this one next class, we can, but some things do cancel right away. We can rewrite all of our powers. This 2 raised to the 2n plus 1, I need to multiply that 2 through and then split things up and see what cancels. All right, so this is our first step in our ratio test. Any questions about that? Okay. I worry about the alternating series test because it's not clear to me how I'm going to know what happens to my bn, my non-alternating part. I'm a little concerned about checking those 2 steps in the alternating series test, so I maybe don't want to do that one if I can help it. Okay. Our second one, somewhere n goes from 3 up to infinity of 2 to the n plus 1 over 3 to the n. Any thoughts on this one? Any ideas? What test might you like to do on this one?
Do another ratio test.
So one thing we could do on this one is we could do our ratio test. And that seems really reasonable because I see a lot of n's in the powers. So that's one possibility. So I set up my ratio, and I look at this and I say limit as n goes to infinity of 2 to the n plus 1 divided by 3 to the n plus 1 times 3 to the n over 2 to the n plus 1. And at this point, I get a little upset because my ratio test is looking really good until I get to here, and this plus 1 is going to make for major issues in terms of canceling. Unless I want to pull out my get out of jail free card and try and use some illegal algebra, I can't do much canceling here because of that plus 1. Okay. So my algebra could get hard. Right. So the ratio test is a good idea and a good first step, and then the algebra gets hard and I get concerned. So I go back up to the series up above up there, and I look at it and I wonder, can I do anything with that fraction up there? All right, Joanna, you're nodding your head. What are you thinking?
You can split it up so it's 2 to the n over 3 to the n plus 1 over 3 to the n.
Yeah, because we only have one term in the denominator, this fraction can be broken up, and so we can write it as the sum of 2 to the n over 3 to the n plus the sum of 1 over 3 to the n. And now this takes care of our plus 1 problem that we had with the ratio test. And so when I look at these two series, both of these are geometric series, and I can figure out the a and the r for both of these. So now we have two geometric series, or I could do two separate ratio tests of those.
Well, couldn't you just do a geometric series just with the plus 1 in there?
With the plus 1 up here, I
Without
can't.
splitting it up?
I'm not going to be able to do that because I'm not going to be able to factor out an a value and then have 1 plus r plus r squared. That plus 1 is really messing stuff up for us.
And when you do the ratio test, then it both has to be the same as well, just like in a geometric.
That's correct. In terms of if I do the ratio test and the first one converges and the second one converges, then the full sum converges. But if one or both of them diverge, then the full series diverges. Good. Okay, other questions on this one? Okay.
I'm not sure on why you can't just pick that limit for the ratio test.
So our first step might be to, I could rewrite 3 to the n plus 1 as 3 to the n times 3 to the first. So I can cancel my 3 to the n's. But where I run into problems here is with the part that looks like 2 to the n plus 1 over this one here. When I rewrite this, 2 to the n times 2 to the first plus 1, I cannot cancel my 2 to the n's because I have that plus 1 added on in both cases. So that canceling would be illegal. If this was multiplication, that would be fine. But with addition, I cannot cross off the 2 to the n's. And so that's going to leave me with some problem areas here.
But doesn't 2 to the n plus 1 grow faster than 2 to the n? Isn't that what's important?
Well, 2 to the n plus 1 over 2 to the n. 2 to the n plus 1 does not grow faster. It's twice as large as this, but they're actually growing at the same rate. For each value of n, you're doubling the top and the bottom. So this ratio is actually equal to 2 over 1. And so thinking about that idea, if you're saying, okay, well this is going to be larger, don't forget that 3 we're dividing by 3, and so overall the ratio would end up being less than 1. So you have to be a little bit careful about how much you're waving your hands. Other questions? Okay. All right, so on this particular series, so what I see here is I see another plus sign in the numerator, and the sign of pi times n, that is not very pretty up there. So, okay, so let's see here. So something that we might need here is,
Split them up again?
we could try splitting them up again. So we could try the sum of 1 over n cubed plus the sum of the sine of pi over 2n over n cubed. Alright, so this first series, what do we know about this one?
P series?
Yeah, this is a P series. P is equal to 3, which is greater than 1, so this series converges. Now the question becomes this next one over here. And so now we have a small issue here, and I think I made a small typo on this one, in that what I wanted was to have that be plus and minus 1, rather than plus 0, minus 0, plus 0, going 1, 0, negative 1, 0. So I didn't really want that. That's a little bit of a problem. But if I write it out, so I'm actually making this one harder than I intended, but it's still maybe okay. Maybe not. Any thoughts?
I was thinking harmonic series for that part.
Well, so if we had an n in the denominator with not an n cubed, then that our harmonic series might make some sense in there.
Test for divergence.
So test for divergence, if I cover up my series symbol and I look at this, then my top is bouncing between plus and minus 1, but my bottom's getting really big, so my terms are approaching 0. So test for divergence is going to work for us.
Is it improper to the point of using L'Hopital's rule?
L'Hopital would be strictly for sequences. And we don't have infinity over infinity here to use L'Hopital.
Integral test?
No, the integral test says that our series must always be positive, and in this case, our terms are sometimes negative. All right, so we've got a small problem here. I'm going to fix this problem in the following way. So I'm going to change this to 2n plus 1 times pi over 2. This was my intended statement. So let's look at this. When n is equal to 1, we have 2 plus 1, which is 3 pi over 2. What is the sign of 3 pi over 2? Pi over 2. 3 pi over 2.
So it would be negative.
Negative 1. Okay. When n equals 2, we have 2 times 2, which is 4, plus 1 is so 5 pi over 2. Top of the circle. So what's the sign of the top of the circle? Okay. And so now if I have this set up this way, our number on the top is going 1, minus 1, 1, minus 1. So this guy is alternating. So now this thing, the top part, goes plus and minus 1 back and forth. So we have an alternating series, and I have a couple of options. What's it?
The absolute convergence test?
Yeah, so one option is the absolute convergence test. And the absolute convergence test says, let's look at the sum of the absolute value of the sine of 2n plus 1 times pi over 2 divided by n cubed. If I throw in the absolute value bars, that plus 1 minus 1 on the top, what is the absolute value of plus or minus 1? Positive 1, and so we get the sum of 1 over n cubed. And what do we know about that?
Convergence.
That converges. It's a P series right here, and so now this P series, where P is equal to 3, which is greater than 1. The series with absolute value bars converges, therefore the original one converges. So that one was a typo on my part, I apologize. That was supposed to be plus and minus 1s, not going all over the place.
So what's the answer to the typo one?
So the answer to the typo one is that we would look at, we would say, okay, well, we have half as many terms now as we originally had, right? Because half of them went to 0. So you still have an alternating series of plus and minuses. And in the end, we can still talk about that one converging as well, but we might need to compare it with using a direct comparison test, which we can talk about. Okay, other questions or comments? Okay, so our next one, over here, we've got n plus 1 over n squared times the square root of n, the sum of all of those terms. When I look at this one, what I see is I see n's all over the place in the base. And so I might ask myself, okay, what do I want to compare this to? This looks like a good limit comparison test. N in the base, which tells me, let's look at the limit comparison test. So I want to compare to, let's see, I'm going to take my biggest power in the top, and in the bottom I only have one term. Now, that denominator, that n squared times the square root of n, I should probably rewrite that. So this is really the series, which is the sum where n goes from 1 up to infinity, of n plus 1 over n, let's see here, this is n squared times n to the 1/2, and so if I add those powers, I get n to the 5/2. You should double check that for yourself. N squared times n to the 1/2. When I add those powers, I get n to the 5/2. So I want to compare it to n over n to the 5/2. I want to compare that series. So if I simplify that series, I have the sum of 1 over n to the 3/2. So remember, when I'm simplifying here, I can cancel out n to the first on the top and the bottom, and that leaves me with an n to the 3/2 in the bottom.
Oh, what do you mean?
How did I do this
Yeah.
part here? So one way to do this is I can think about writing n to the 5/2 as n to the first times n to the 3/2. So if I add these two together, it gives me 5/2. Another way to think about it is I can think about subtracting the two powers. And since the one at the bottom is larger, that's where my remaining pieces go. Josh?
Can't you do a p-series with that, since that 5/2 is constant?
That's a really good question. If I wanted to do a p-series with this, as it's written right here, I could not do it, but I could split this up into two separate sums, and then this first one would be n over n to the 5/2,
That, and then 1 over.
and then 1 over n to the 5/2, so you'd have two separate p-series, and you can do that as well. Good. Good. So one option is limit comparison test. The other option is split this up into two separate series and look at each one separately, and they turn out to be two p-series. Okay, other questions or comments about that one? All right, and our last one. The sum where n goes from 1 up to infinity of n over n plus 1. So when I look at this, my very, very first thought might be, oh, I see an n in the base, let me do a limit comparison. So let's do a limit comparison test, and I would compare to, yeah, I'd be comparing to the sum of n over n. I look at my top power on the top and the bottom, which means I'd be comparing to the sum of a bunch of 1s. Now, that's a little bit weird, and if I want to continue on this route, I can certainly use a limit comparison test. If I add up an infinite number of 1s, what's my sum going to add up to? Infinity, yeah. So this particular series diverges, and I can set up my limit for my limit comparison, and I can compare to the sum of a bunch of 1s. But that ends up being maybe not the best option. An easier way to think about this problem is, if I think I want to use a limit comparison test, and I end up comparing to an actual number here, then what that says is that instead, I'd like to look at the terms and say, let's look at the terms n over n plus 1, take the limit as n goes to infinity, I get a value of 1. My terms do not approach 0, so my series diverges. So the test that's actually quicker and easier is to say, okay, let me look at my terms. my terms, if I convert my series, my terms do not approach 0, so therefore by the divergence test, series must diverge. But in my head, I kind of was messing around a little bit, and again, in my head, I'm thinking, oh, I've been using the limit comparison test, I'd like to use that test. If I get to that point and I say I want to compare to the sum of one number or 1/2 or whatever, I'm adding up a particular number an infinite number of times, then I might say, let me back up a little bit here, let me look at the divergence test and see what happens.
So that one, the one before is just a p-series and it converges, right? Because the p is greater than 1?
This one here?
Yeah.
So if my comparison for my known series converges, and then I have to do the limit of the mystery term over the known term and do that ratio, or do that limit.
Okay, so you can't just go to a p-series from right there, 1 over n.
So what this says is that this is a p-series where p is equal to 3/2, which is greater than 1. So our known series converges. But from that, we actually need to convince everyone else that our choice for the known series is in fact comparable to the original. So you've got to look at the limit of the mystery terms divided by the known terms. So we're not done with this particular problem.
So it's just that divided by that.
And then take the limit as n goes to infinity.
Alright.
Yep. Good. Okay. So take these home and work through a few more of them, and we'll talk about those as part of our review in our next class. All right, so for our last 20 minutes of class today, I'd like to talk about the remaining portion of new material for exam 3. All right, I'd like to talk about section 8.5, which is power series. And so the series given by the sum where n goes from 0 to infinity of Cn times x to the n. So check out what I have written here. I've got a c with a subscript n and an x raised to the power of n. Now, what this series says is that, okay, I'm going to start at n equals 0, and I'm going to plug 0 in everywhere I see an n, so I have c subscript 0 times x to the 0, which is 1, so I'm not going to write that. And when n is equal to 1, I have c1 x raised to the first power plus c2 times x squared plus c3 times x to the third plus c4 times x to the fourth. And this is going to go on forever and ever and ever because we're going up to infinity. And this series is called a power series. And I have a second version of this, which looks like the sum where n goes from 0 to infinity of Cn, and instead of just x raised to the n, I have the quantity x minus a raised to the nth power. And so this one looks like C0 plus C1 times x minus a plus C2 times x minus a, the quantity squared, plus C3 times x minus a, the quantity cubed, plus C4 times x minus a to the fourth, plus dot, dot, dot. And this guy is also called a power series. Now, what you might notice about these two examples here are that we have these C values, and these C values, C0, C1, C2, these are our coefficients. And so the C's, C0, C1, C2, etc., are constant coefficients and the thing that's different about this series than all of the other series that we've been looking at is that these series have variables in them. These series have variables, meaning the x in them, and the x is raised to a power. That's why these are called power series. The variable that's part of our series is raised to a power. Now, the difference between these two power series is that the second power series, every time I had an x, I actually had x minus a, not just an x. And so the second power series is called a power series centered at x is equal to a. And our first one up here, where we didn't have the minus a as part of the series, well, this is called a power series centered at x is equal to 0. So up here I could have technically written x minus 0 squared, x minus 0 to the third, etc. Alright, so everything that we've been doing for the last 2 weeks has been questions about, does a series converge or diverge? And now we're throwing variables into our series. And so the big question that we are asking here is not does the series converge, but for what values of x will the series converge? What values of x will our series converge? Alright, so let's look at an example. Our very first example is going to be an example where the CNs are all equal to 1. So the coefficient C0 is equal to 1, coefficient C1 is equal to 1, coefficient C2 is equal to 1. And so what we'd end up with is we get the sum where n goes from 0 up to infinity of 1 times x raised to the n. And so when I look at this, I say, okay, I'm going to start writing out some terms. My first term is 1 times x to the 0, which is 1. My next term is x. My next term is x squared plus x cubed plus x to the 4th plus x to the 5th plus dot, dot, dot. Alright, so I've got a power series centered at 0 because I don't have, it's not x minus some number raised to the n, it's just x raised to the n. And I write this out and I have all these terms right here. Now, when I look at this series, notice that I have x raised to the power each time. And I look again and I say, you know, this series looks awfully familiar. What kind of series does this kind of look like? It looks an awful lot like a geometric series. So we might note that this is a geometric series. Now when I go to try and factor something out, I already have a 1 in my first term, so I cannot factor anything out. That tells me that my a value is 1, and my r value is x. Alright, so what do we know about a geometric series? For what values of R does our series converge? Yeah, the size of R has to be less than 1. And so in a geometric series converges when the size of R is less than 1. So for our example, our series converges when the absolute value of x is less than 1. Another way to write absolute value of x is less than 1 is to say that x is strictly between -1 and +1. And because we have a geometric series, our series converges to a over 1 minus r. A is 1, and r is equal to x. And so our series converges to 1 over 1 minus x. So I've just thrown a bunch of stuff up on the board, and I want to rewrite it down. I want you to think about what I just said here. What I've just said is that 1 plus x squared plus x cubed plus x to the 4th plus ... is exactly equal to the function 1 over 1 minus x as long as x is between -1 and 1. Alright, so this is an example of a power series, and I'd like to show you what the heck this means in terms of a picture, and we'll use our last 5 minutes for this. Infinite sum. This is our series. And what I'm going to do is make a table that has first the first term, and then the first plus the second, first plus second plus third, first plus second, so 1 plus x squared plus x cubed, etc. And what we're going to do is that we are going to plot each of these partial sums. So take a look at this blue curve. This blue curve right here, this is our vertical asymptote. That's not really part of the function. But that curve is 1 over 1 minus x. And this purple line is starting here at just y equals 1. When I press the forward button, this is 1 plus x. Here's 1 plus x squared. 1 plus x squared plus x cubed. So now I'm going to go ahead and hit the play button and watch what happens as I add more and more terms. As the slider moves to the right, we add more and more terms. Watch what happens with our series. Now, a few things are happening with this. Number one, this left side is flopping up and down like a fishtail. And so that makes sense because we're going from an even function to an odd function to an even function to an odd function. So the even ones are both pointing upwards, and the odd goes like this, one up and one branch down. So that's why that end is flopping up and down. But what you'll notice here is here's -1, here's +1. Within this interval, when x is between -1 and +1, these partial sums are approaching the value of our function 1 over 1 minus x. So let's pause this one and see what we headed. Okay, so between -1 and +1, our curve is matching exactly. Outside of that interval, this guy is flopping all over the place, and it never settles in on our curve 1 over 1 minus x. And over here on the right side, we never even hit this portion of the curve over here. And so what this is saying is that this power series converges to 1 over 1 minus x for the interval from -1 to 1. This interval is called our interval of convergence. And what we're interested in is being able to use a power series to draw a picture of a function and use that power series instead of the function itself. So in this case, we care about, so I can even put more on here. I can maybe change to, instead of having 10, I could put in 100. So, oh, they didn't like that so much. Okay, maybe not so much. How about 50? So here's my first 50 of my terms. There it is. Oh, there we go. There we go. Going all the way up to our very last one is all the way up to blah, 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 plus x to the 50. And so now when I look at this, and I hit play, I mean, look at what's happening there, right? Once you get to a certain point, it looks just like the function, but only between -1 and 1. Outside of that interval of convergence, these terms are flopping all over the place and looking like crazy. But in between -1 and 1, our power series is converging to our particular function. So that's what our question here is. Now we are throwing in a variable so that our power series becomes a function, and we ask, what does this function power series converge to? Well, in this case, converges to the function 1 over 1 minus x, as long as we're between -1 and 1. Okay, so that's our introduction to power series. We'll talk more about them next time.